So I'm going to be talking about some work I've been doing with Hong Liu and Nati Zeiberg in 2 papers on FTH. There's some closely related works by Fobinger and McGreevy and Horowitz and Polchinski. And, whoops, what happened? Okay. New technology. There seems to be some impression that a lot of people have that there's a big disagreement among these papers. And let me say at the outset that as far as I'm aware, we're all in agreement on the physics that we'll be discussing. So I'll give you some introduction and motivation, talk about the geometry of some time-dependent orbifolds, say a little bit about solutions of the wave equations on them and twisted sectors, and conclude and make some allusions to tomorrow's talk. As you all know, the nature of time and general relativity is subtle, and there are deep and well-known conceptual problems. So one might hope that in exactly solvable string backgrounds, and string theory is a theory of quantum gravity, one might hope to address some of these problems. But in trying to think about string theory in interestingly time-dependent backgrounds, you rapidly run into a number of complicated conceptual and technical problems. And among the many problems, I'll be focusing on one, that of back reaction. I'll actually mostly be discussing kinematics today, and a companion talk by Nati Zeiberg tomorrow will focus more on the dynamical issues. Now, there are 2 well-known sources of back reaction effects. If you don't have supersymmetry, as you generically don't in time-dependent backgrounds, there could be tachyons and infrared instabilities. And if you have closed causal curves, then there are potential infinities in loop amplitudes and in evaluating expectation values of composite operators. In this talk, we're going to look at some simple models where both of these effects are under control, and nevertheless, string perturbation theory is not well defined. And it's very simple to explain. It's that we'll have there'll be a shift around couple G, and that leads to divergences in string perturbation theory, even at tree level. On the positive side, we'll also find that there are null branes, time-dependent backgrounds where string perturbation theory is well defined, and that leaves some room for further progress. Now, time-dependent backgrounds are very difficult to work with, so it's a good idea to work with something exactly solvable like an orbifold. And so we'll look at orbifolds of Minkowski space by a discrete subgroup of the Poincare group. This is a class of models introduced by Horowitz and Steiff about 12 years ago. And recently, it's been the subject of much interest in many papers. The very simple example of what we're discussing is to take the orbifold group to be Z with generator G0, acts trivially on 8 dimensions, non-trivially on 1 + 1 dimensions. Here are the light cone coordinates. G0 to the n acts as a discrete boost. So we have, so what should we take for our orbifold group, gamma? Well, some criterion you might want to impose are time-dependent background, because that's what we're interested in. You might want to have unbroken supersymmetry, and we'll ask that there be no closed time-like curves. And some immediate implications of that are, first of all, from the unbroken supersymmetry, a null killing vector, so we can use light cone gauge. We have no particle production, so we have a lot of simplifications. We are discussing a very simple version of a PP wave, so we're on topic. And from results of Figueroa-Farrell, somewhat less obviously, it follows that gamma must be a certain discrete subgroup of this extension of spin 7 by 2 Euclidean groups. So when you start to look at such orbifolds, if you look at examples, you start to find some strange things happening. In the case of Euclidean orbifolds, we really know what are the physical criterion, physical consistency criterion we want to impose to have a good model. It's essentially anomaly cancellation. But we don't know what the criteria are in the Lorentzian case. For example, fixed points, unlike the Euclidean case, fixed points can lead to pathologies. Even if you don't have fixed points, you might have closed causal curves, and these can also lead to pathologies. Even if you don't have fixed points and you don't have closed causal curves, you can have stranger phenomena like nearly closed null curves. That is, an infinite sequence of space-like geodesics whose lengths tend to 0. This is another kind of, this will lead to pathology. You can have explosive degeneracies in the twisted sector, by which I mean the sum of the partition functions over the twisted sector can diverge. And then you can have this problem of blue shifts. And this is the one I'm going to be focusing on, because this is probably a generic effect. So, indeed, in the rest of the talk, the orbifold group is just going to be the integers, z. It's generated by g0, and g0 acts as follows on 10-dimensional Minkowski space. X plus and x minus are like cone coordinates. X vector is in the 8-dimensional transverse plane. So g0 as a function of lambda of v and r acts by a shift in the transverse space. And then the dependence on v here gives me a parabolic Lorentz transformation. Now, if we only have one generator, we might as well simplify this as much as possible. So by conjugation, we can take v to point in the 1 direction and r to point in the 2 direction. And if v is non-zero, you can even set it to be 1. Nadi wants to set it to be 2 pi. Well, it doesn't matter. And actually, the reason I wrote this in a slightly more general way is that many of the considerations that I'm talking about generalize immediately to multi-generator groups and even Heisenberg subgroups of the isometry groups of PP waves. But let's focus on this one generator case. So it acts non-trivially on 4 dimensions. Here's the action again. x2 shifts by nr. X plus, x1, and x minus have this parabolic transformation. What does this space-time look like when I take the quotient? Well, it's foliated by surfaces of constant x plus. There's a circle in the surface of constant x plus, and the radius of that circle is easily calculated by taking the distance between x and its image, and that's x plus squared plus r squared. So we have this kind of hourglass shape. This space-time was called the Null brane by Figueroa, Farrell, and Simon because it can be interpreted as generalized flux brane. So we'll adopt that terminology. Now we're actually also very interested in the r equals 0 case, which we'll call the parabolic orbifold or the Null orbifold. In that case, the action on the transverse space is trivial, so we just have this parabolic Lorentz transformation. And the space-time now looks like a double cone. Well, that's a bit of a lie, actually. That's only the accurate picture away from x plus equals 0. In fact, the space, the honest-to-God quotient space is a non-Hausdorff space near x plus equals 0. And since string theory really constructs strings on the group quotient, we probably should take that seriously. Well, that's all I'm going to say about the geometry. Now, what about the wave equation on the orbifold? Why are we interested? Well, we want to start calculating, thinking about physics in this double cone. Do strings get from one cone to the other? And what about the S matrix and all of that? Well, the first step is to solve the wave equation on the orbifold, because solutions will be the untwisted vertex operator in the quantized string. Okay, so we all know how to solve the wave equation. We introduce plane waves, and we'll be thinking of p upper minus as a function of p vector and p upper plus. And then the general solution of the wave equation is going to be a sum over momenta. We'll fix p upper plus, but integrate, we'll need to integrate over the transverse momenta. Okay? Any question about the notation here? Good. So now a small calculation shows that these wave functions are invariant under this orbifold transformation if and only if the momentum space wave function satisfies this crucial equation. So wake up. This is the equation you need. This says that if you shift p by v times p plus, then up to some phase factor, depending on the shift r in the transverse space, you get chi of p. OK. So now let's analyze what that says in detail in the d equals 1 and d equals 2 case. In the parabolic orbifold, we have strict period. So we can write a basis of states by introducing, you can't see that, by introducing plane waves. These plane waves have this quantized period here, and this is what Nadia will be referring to as J eigenstates in his talk. In the d equals 2 case, a shift in P1 is a phase depending on P2. So a basis of states is obtained by taking an arbitrary function of P2, a periodic function of P1, and this Gaussian phase factor. OK, now that we understand what the solutions of the wave equation look like, we can see there are two sources of trouble. One is that the wave functions can be singular, and the other is that they can have too much support at large energy. And in Nadia's talk, they to infinity is at string tree level. A little bit on points. First of all, well, the functions of the most single line is to the smallest values. That's at x plus equals 0. And at x plus equals 0, this wave function just becomes a Fourier transform of this momentum space wave function. Okay, so in the parabolic orbifold case, chi is just a plane wave. So you see that indeed the wave function becomes singular. It becomes a delta function. We call this the focusing effect. The wave functions are focused onto a certain lattice in the transverse, in the x line. Whoops. In the case of the Null hand, after putting some constants, the wave function, we can substitute it into take its Fourier transform, and the wave function, the resulting wave function, is completely smooth on the x plus equals 0 slice. This generalizes rather nicely to all subgroups of the Heisenberg group. The smoothness of the wave function is equivalent to the absence of nearly closed null curves. OK, so much for the singularity. What about the problem that there's too much support at large energy? Well, you see, the wave function is quasi-periodic in p vector. And the energy is going like p vector squared, so that spells trouble because gravitons couple to energy in intermediate lines. And indeed, in the parabolic orbifold, it does spell trouble. You have strict periodicity, but in the null brane, it's more subtle. In the null brane, you can choose an arbitrary wave packet here, which is of rapid decrease. The wave function in P1 here has to be periodic, so that won't help you. But there's a Gaussian fall-off factor. So the net result is that the amplitudes will be finite in the null brane. So the regularizing the geometry does also regularize the S matrix. Let me say a few quick words about twisted sectors. There are two results here. First is that there's an interesting exchange algebra in the twisted sectors. And secondly is that there are twisted states. So I don't want to go through details here. There's too many details. But what does one does twisted sector where J is the data orbifold, write things in terms of harmonic oscillators. And it turns out you get some rather non-standard commutation relations for the harmonic oscillators. leading to an interesting exchange algebra for the chiral currents. So that's suggestive of many things to many people, and there's certainly, I would suspect that some interesting things could be done with that. Now, the other result I mentioned is that there are physical twisted states. You start out by constructing a sensible ground state in the twisted sector, and then you construct some DDF operators. They're a little more complicated than the usual ones because they have to descend to the orbifold, but they exist. They give you positive norm states. And then you can confirm this with a one-loop analysis. And this is not trivial because Nekrasov found in the hyperbolic, in fact, there were no states in the twisted sector. And a big open problem left by our work is whether or not these physical twisted sector states have an important effect on the qualitative physics. Well, there are a lot of related models. Obviously, we could choose other discrete subgroups of the group G, or we could take orbifolds of PP waves, where you also have this Heisenberg-type group. I mentioned that that the null brane is a generalized flux brane, so there are connections to Melvin models and flux branes. And there's also connections to BTZ black holes. In fact, there's a rather direct connection to the m equals j equals 0 BTZ black hole, which is a quotient of the universal cover of SL2R by G0 acting by conjugation. So there's this parabolic Lorentz transformation. It acts by conjugation. That's this space. Now, since it acts by conjugation, it fixes the identity element of the group. So you can localize to the Lie algebra. And that localization to the Lie algebra gives you the Lie algebra divided by G0 acting by conjugation. And that's exactly the parabolic orbifold. So physically, what we're doing is, here's the m equals j equals black hole. We're focusing on a scaling region near the horizon. Now, the way I've explained the possibility that there's trouble leads to a conjecture or more of a worry, which is in general, you can worry that if you gauge WZW models by non-compact gauge groups, it's not obvious that this will lead to a well-defined string perturbation theory for exactly the kinds of reasons I've mentioned for the orbifold. Okay, so to conclude, we've got a class of models with weak coupling, with supersymmetry, all orders of alpha prime under control, and yet, to my surprise at least, not all is well. String perturbation theory is not necessarily well defined in such backgrounds. On the positive side, we see that there are indeed good time-dependent orbifolds, namely the null brane with R positive. And so that suggests the obvious open problem, which is what are the conditions we want to have to guarantee that we have a good time-dependent orbifold. Another interesting new phenomenon related to all this is that of so-called UV-enhanced IR divergences. And you'll hear more about that tomorrow, same channel, same place. Okay.
Questions?
Kamran Rafa from Harvard University. In usual orbifolds, twisted sectors, as you noted in your transmissions, are crucial. Here you said you did not consider twisted sector. You studied.
We showed that the physical states on the twisted sector exist. They're crucial for things like modular invariance.
Right.
And that's what I was alluding to when I said we checked it with a one-loop analysis. I mean, we did the one-loop computation very carefully, both from the trace point of view and the path integral point of view, checked modular invariance and all of that. So they're there.
But the perturbation breaking down will not be resolved by these guys, in other words.
Well, we don't know.
Oh, so it could potentially
We don't know. I mean, it's hard to imagine a mechanism whereby the twisted sector production is certainly not.
Okay, let's